right, so we'll get started and expect that more people will trickle in. So it's my pleasure to welcome you to day 2 of POPL and to this first talk. And Shankara is going to give the talk on semantic code refactoring for abstract data types.
Hi, everybody. I'm Shankara, and I'll be presenting my work, semantic code refactoring for abstract data types. And this is joint work with Yuepeng Wang from Fraser and Işıl Dillig from UT Austin. So abstract data types, or ADTs, are a commonly used abstraction in software development. So recall that an ADT consists of a set of method declarations as well as constraints specifying aspects of their behavior. So for example, an ADT for a stack will have declare various methods like push, pop, etc. And will also come with certain constraints, like pushing an element and then popping it will return that same element. Now the concrete data types, which we refer to as the ADT implementations, may use different data representations to perform the operations specified by the ADT. So for example, the stack ADT can be implemented using an array or a linked list. And these choices in data representation can yield significantly different implementations. And this leads to the main challenges when it comes to actually refactoring the data representations of an ADT implementation. So when we change the data representation, large portions of the implementation may need to be changed. And these changes oftentimes cannot just be copy and pasted across the different methods. So that makes it kind of a challenge when it comes to refactoring. So to help illustrate some of these challenges, here's an example refactoring we found on Github in the bitmap tracker class taken from a popular Java repository called Glide. So you don't need to understand everything that's going on here. I'll just walk you through the relevant portions. So the developers repurposed 2 fields called pending and counter, which keep track of bitmaps, essentially, and also the pending bitmaps. And they refactored into a single hash map, mapping the hash code to this inner tracker object. And as a result, several methods needed to be changed, and only small parts of the code ended up staying the same, like getting the hash code of the input bitmap, but the rest had to be essentially completely re-implemented, and it's also true for the rest of the methods. And if we look at the changes made at each function, we note that while both implementations end up trying to see if a corresponding bitmap has already been tracked, they do completely different things. So for example, on the left-hand side, it basically will create a tracker if it doesn't already exist, whereas on the method on the right only does stuff if there's something already associated with that hash code. And similarly, each method actually invokes different methods on the tracker, if it exists. So on the left, the code calls this acquire function defined within this inner tracker object, whereas on the right, it calls this release. And finally, the code modifies the actual values of the data representation in different ways. So on the left, it will actually add an entry to the hash map, whereas on the left, it only removes an entry if release returns true. And so the key takeaway here is that the refactoring is kind of highly dependent on the semantics of the underlying data representation, as well as the semantics of the original method implementations. And not unsurprisingly, manual refactorings can introduce new bugs into the program. And we actually found a real-world case where a refactoring introduced 2 bugs, both of which were actually resulted in memory leaks. Now, with this in mind, ideally, we would like to automatically refactor an ADT implementation given a change to the underlying data representation. However, in practice, there's many actual possible ways to refactor an implementation. How do we know what the intended one actually is? And so one thing we actually observed is that the old and the new data representations are oftentimes expected to stand in some kind of relation with each other. So for example, suppose you took implementation on the left, which is a hash map from ints to strings, and the new one actually just tracks the inverse mapping. Then we would expect the following relation to sort of hold between these two representations, where every key value entry in the original map, there's a corresponding value key entry in the reverse, and vice versa, right? And we refer to these kind of invariants as a relational representation invariant, because it holds between the two implementations. And for our purpose in this talk, RRI, relational representation invariant, is a Boolean function that relates the values of the old and new representations. And what we require in our work is that the RRI should be precise. So what I mean by that is that it should given a value of the old ADT implementation, an instance of the old implementation, there should be a unique instance or values of the new representation that satisfy this RRI. And it should also be total. So for every instance of the original, there should exist at least a value for the new representation that satisfies the invariant. And it's essentially what this is really saying is that there should be some kind of function that maps the old to the new. So with this in mind, we can define this refactoring problem. So given an ADT implementation I with fields f and methods m, and a set of fields f prime corresponding to the new representation, we want to generate a new ADT implementation such that for every method in the original, there's a corresponding method m prime in the new one, such that one, the behavior of the two ADTs should be observationally equivalent, and they should sort of preserve this relational representation. So if it holds before a call, it should hold after a call. And so to do this, we developed a tool called Revamp, which takes those three inputs and synthesizes a new ADT. And if there's a timeout, it will return unknown. And at a high level, the Revamp performs this refactoring modularly by synthesizing new implementations one at a time. And this is for scalability. It also performs top-down enumerative search to actually synthesize the bodies of the functions. And it uses PCFG to guide the search. But the core contribution in this work is a novel instance of a novel inductive synthesizer within a CEGIS loop that really accelerates the synthesis. And I will describe that in the following slides. So our actual inductive synthesizer consists of three key ideas. So first, there's at its core, this kind of synthesis problem is a relational synthesis problem, and we can kind of reduce this generally complex synthesis task into a case of programming by example. And this reduction helps us in two additional ways. So first, we can, given this reduction to PBE, we can actually leverage symbolic reasoning to infer useful code snippets and augment our grammar with those. And then we also introduce this notion of partial equivalence to essentially accelerate the search frontier using some kind of component-based synthesis. So to help illustrate these ideas, I will use the following working example. So on the left is the original implementation of this rectangle ADT. And it consists of several methods. And the one I'm going to focus on is this scale and flip. And the original ADT consists of three fields. There's this LC representing the lower left-hand corner, as well as the height and the width of the rectangle. Now, suppose we want to change the data representation to only have these four fields, which is like the minimum x and y values spanned by the rectangle. And we're also given the following relational representation invariant, which says what you would expect, that the max x minus min x is equal to the height max y minus min y is equal to let's flip it around. And now we will show how we synthesize the following new implementation on the right. First, I'll just briefly go over what this method is actually doing. It's relatively straightforward, but this should help for following along. So at a high level, this method essentially scales down the rectangle's height and width by these parameters h and w, respectively, and then potentially flips them over the x-axis, x or y-axis. So suppose we have the following instance located in the upper left quadrant with height 3, width 2, and we are given the following inputs. Then the function will first transform the rectangle by shrinking it down into this unit square, and then flip it over the y-axis and then over the x-axis, yielding the following output instance. So now I'll go over the first key idea, which is reducing the problem to an instance of PBE. So recall that we're doing this kind of CEGIS loop, and suppose we, we synthesize an incorrect implementation. So then our verifier will give us this counterexample input. So this is some input where that RRI fails or is not observationally equivalent. Now, then we can take this counterexample input and actually just run the original implementation to give us the output instance of the original ADT, right? Now, what can we actually infer about the output of the new ADT? Well, so recall that we require this precise RRI, right? So there should be exactly one instance of the new ADT that satisfies this invariant. So we will try to find that basically. So given the RRI and this output of the original, we essentially infer what the corresponding value should be for the new ADT. And we do so using essentially symbolic execution on the RRI. And you could use SMT if it's loop-free. Okay, so now that we have this IO example, what can we actually do with it? So we use this IO example to infer useful code snippets. So given this IO example, we can basically do the following. So we can actually execute the original implementation. And if we take the path that the execution goes on, we get and encode it, we get the following formula, which basically describes how the old fields are updated in the original implementation. So the prime variables describe the states at the end. Now, if we can also get the corresponding path satisfied before and after the call in the RRI. So the path taken by the input values describes how the old and new fields are related prior to the call. And finally, the following path describes how the old fields should relate to the new ones after the call. Now, given these three formulas, we can eliminate essentially the old fields, and we get a formula that tells us how the new fields should be relate to how the new fields after the call relate to the new fields before the call. So it sort of tells us how to update the new fields. So we get a formula like the following, and note that it's actually very similar to the actual new implementation. And so what we do is, given this formula, we use syntax-directed translation along with static analysis to augment the grammar with useful code snippets. So we'll mine statements like the following, and as well as some expressions. And then finally, I'll talk about the last key idea, which is accelerating the search via partial equivalence. So now we have this IO example. And suppose during synthesis, we synthesize some of these incorrect programs shown on the left. So the one on the far left correctly updates the x values, but not the y's. And the one on the right correctly updates the y values, but not the x. So normally you would just throw these programs away. But since they satisfy some of the fields, there's a good chance that they're going to be used in the final solution. So rather than throw them away, we actually combine them using a kind of component-based synthesis to accelerate search. So we'll then generate additional programs like the following, right? And so that allows us to quickly build up complex solutions. Okay, so to evaluate Revamp, we manually gathered 30 ADT refactoring tests from Github. And they were taken from popular Java repositories. And in total, this required refactoring around 146 methods. And we manually wrote these representation invariants for all 30 refactoring tasks. So the key takeaway is that Revamp automatically refactored 29 out of 30 implementations and 144 out of the 146 methods. On average, the refactoring took about under 5 minutes. And then we manually, even though manually inspected the synthesized ADTs afterwards and found that they were equivalent to the ground truth, ones written by the developers. And then we also compared against a few baselines, JSketch, Volt, and ChatGPT. So for JSketch, we manually wrote generators using and also used the IO examples generated by Revamp as the spec. And then Volt is another tool that does a similar task called data structure refinement, and we replaced our inductive synthesizer with Volts. And then finally, we used ChatGPT in a one-shot learning setting. So we provided it the original implementation, the RRI, and asked it to generate a new implementation that preserved the existing behavior. And so basically, Revamp was able to solve about 20 more benchmarks than the baselines, and 50 more, refactor 50 more methods than the next best baseline. So in conclusion, we proposed a new algorithm to automatically refactor ADT implementations given this RRI, and that there's 3 key ideas we use. We reduced this inductive synthesis problem to an instance of PBE. We also use symbolic reasoning to infer useful code snippets, and we leverage this partial equivalence with respect to the new data representation to accelerate search. And we evaluated it on real-world refactoring tasks, demonstrating its effectiveness. And with that, I'd be happy to take questions. Oh, sorry. I'm sorry.
So we have time for a question.
So when you curated the examples, the tasks that you found, was the assumption that the RI would be a function realistic, or did you have to throw a lot of examples out because you couldn't have an RI which was actually a function for that?
Oh, yeah. So I mean, there was, we actually describe our methodology a bit more in the paper, but essentially, for the most part, it was relatively straightforward to write something that was an RRI. So the hard part was just trying to understand understand the code basically from the diff and see what the developer is intending to do. But once you do that, it's actually, I think it's relatively straightforward. We also have some additional tools in Revamp to check whether something is an RRI. So yeah.
We can do another question. Can you unplug your laptop and we'll?
Oh yeah, sure. So.
How stringent is the requirement of unicity of the representation? Many data structures, they have observational equivalence. For instance, if you add something, then you withdraw something, then it's not exactly the same data structures, but it's observably equivalent. Do you really have to have everything internally exactly specified, or just observationally?
So you could use your spec as just purely observational equivalence, but those 2 bugs I mentioned, the problem is if you just observational equivalence still is quite kind of under specifying correctness. So the bugs that I mentioned, technically those implementations were observationally equivalent to the original one, but they were due to a developer not removing entries from hash maps. So that doesn't change the observational equivalence, but that's nevertheless buggy. So I think providing this precise RRI is kind of good to eliminate those kind of potential errors when you're refactoring. Yeah. Yeah, that's it.
All right, let's thank the speaker.